For my students, we're going to do exactly two types of application problems involving integrals for Calculus 2, and work is the first kind. I've chosen it because it's a simple thing to define, and I think it's pretty intuitive how it works. Well, let me give you an idea what we're talking about here. Suppose I wanted to lift a 10-pound weight four feet off the ground. The work required is W equals F times D. The F is the force, times distance. So in this example, force is the same as weight. So I have 10 pounds, which we denote by LB, times distance, and that was 4 feet. So the total work needed for this is 40. Usually it's said foot-pounds. It doesn't matter if you say pound-feet, but most people say foot-pounds. We typically do that first. I know I put 2 zeros, but only one. So now most people don't use feet and weight like we do, in America that is. Everybody besides practically America uses the metric system. So in the metric system, the unit of force it's not pounds like we use, it is the Newton, obviously named after Sir Isaac. And it's just a capital N to denote the Newton. Distance is, of course, probably measured in meters. So the way this problem now, if I restate a similar problem, to lift a 10 Newton weight 4 meters off of the ground, requires W equals F times D, which is 10 newtons times 4 meters, equals 40 Newton. I don't know if I have to put a dash in or not. I don't know if it's just NM or... So it's 40 Newton meters. Usually 1 joule is replaced by 1 Newton meter to keep the units in line. So it will require 40 joules of work. This is a very simple application of that idea. You're lifting an object straight off of the ground 4 meters, and that's all there is to it. Now we're going to apply this principle, but we're going to do it in a very specific case, because I want you to see how the idea breaks down. I am not interested in actually teaching you physics, but just the calculus required to do these type of problems, because they work so well with our Riemann sums. You'll see as I get going here. So here's what I'm going to try. Suppose we have a rectangular swimming pool. That has dimensions. Let's say 15 meters wide, 25 meters long, and 2.5 meters deep. So as you can imagine, at the end of every season, they drain these pools. I think the drains are located at the bottom of the pool, but supposing in this example that they're not. Okay, so how much work is required to pump all of the water out of the top of the pool? So these are the kind of problems we're solely going to be interested in, is problems like this. Draining. I think sometimes I play around with the liquid, but not much. Usually it's just water. How much work is required to pump all of the water out of the top of the pool? I think a picture is in order. Let me draw a picture of what the pool looks like. If you want to give it the complete three-dimensional effect, you can put dashed lines to indicate where it would go if you could still see it. In any case, so here's my pool. It's 15 meters wide, it's 25 meters long, and it has a height or a depth, whatever you call it, of 2.5 meters. So I keep thinking feet, but 2.5 meters is taller than most humans. In any case, how much work does it take to remove all that water out? Now, come back to the equation that I had before. This amount of work. Work equals force times distance. That formula is not directly applicable here because you are not taking the entire quantity as a block and lifting it out. The water has to be siphoned out or pumped out a little bit at a time. So let me write, this is important. So you cannot use work equals force times distance directly because the pool is not a solid that is lifted out all at once. Let's say lift it out as one chunk or one piece. Instead, we siphon it out over a period of time. So here is the way the physicists do it is very interesting. I like it because the way it sets up for integration. Here's what we do. We take and we slice the water into n equal slices. So let me draw the picture again. I may exaggerate some dimensions so that I can make it visible to you. So here's my pool. And what we're going to do is slice it up into thin strips of water. Let's see if I can make that go back here. There's slice number 1. Then I'm going to slice it again. A thin slice. There might be slice number 2. Here comes slice number 3. Well, you get the idea. Continue down here until we get to slice K. So, let's call this, we'll call this slice 1, slice 1. This will be slice 2. That'll be slice 3. And then I'm getting to slice K. So I'd like to get the lowdown on slice K. So let me pull it out. Slice K takes the following form. It's thin. I'll try to indicate the thinness here, but I do want to exaggerate the dimensions so that I can at least label it. Now notice these slices, they're all the same width and they're all the same length. All these slices are 15 meters wide by 25 meters long. So I've got those are always the same thing. But what we do here is we call the thickness equal to delta y. The reason why I'm using y is because we are lifting the water out of the pool. And the way it's imagined is this. Instead of slurping it out through a straw or something like that, we imagine lifting slices of water out as one unit. So lift each slice of water out as a single unit. So what that means is then the work done to lift that slab, to lift that slice, we'll call it W sub K, and that will equal force sub K times the distance sub K. I'm using these K's because the force that I'm going to use will be applied to this one sheet of water, and the distance is how far this sheet of water has to go until it gets to the top of the pool. So I need to fill in these things. Let me backtrack for just a minute and look at force. The idea is if this is really thin, really small, then we can treat it as one singular unit when we lift it out. Force has three components. The force F equals volume times density times gravity. And I'll go ahead and put these things in. The volume's easy enough. Volume of slice K. So we'll call it V sub K is going to equal, well, what are the three dimensions? Length times width times height. We have 15 times 25 times delta y. So we got 15 meters times 25 meters times delta y meters. This equals 375 delta y meters cubed. Density. And specifically, we're talking about the density of water. It's the easiest one in the world. We use the Greek symbol rho. That equals 1,000 kilograms per cubic meter. And then there's gravity. G equals 9.8 meters per second squared. So I'm not going to bother with these things, to be honest, until the very end. They're just constants, and usually it's best to just throw them on at the end. But let me go ahead and see what my kth force is. So these are the same no matter what. In fact, this is the same for all the k's anyway, so I could have just called it volume and not worry about it. Because if you'll notice, if we uniformly slice this in thicknesses of delta y, it makes all the integrations easier, it makes everything easiest, and you know from what we've talked about before that no matter how you slice it, you'll get the same answer. So if I go back, these are all supposed to be the same thicknesses and everything. They're like sheets, probably some more as you get to the bottom. You start S1 and you'll end, the last spot that you'll get to will be S sub n. So anyways, my F sub k, or the force on the kth one, is F sub k equals my volume. I've got that, 375 delta y meters cubed. And then I need my density. That's the 1,000 kilograms per meters cubed. I'm just going to put rho. But that was in kilograms per meters cubed. I don't know if the constant includes that in it or not, but I'm putting them there so you can see what happens. And then the last piece is gravity, 9.8 meters per second squared. I purposefully have put these units like this so that I can do some canceling. For example, this meters cubed cancels with that meters cubed. And it looks to me like what I have left over, a kilogram meters per second squared. This equals, then actually I'm not going to, let me erase it. I didn't mean to put the G in there just yet. It's actually going to be easier if we don't use the numbers until we get to the very end anyways. 375, you don't have much, it's better than writing this stuff out to put the 375. So I'll put my 375 delta y. Actually, I'll put the delta y last. I'll put 375 rho g delta y. And now what are my units that I have? I have kilogram meters per second squared. So that's the force that was required to lift that one slice up. How far did that slice travel? Let me draw an exaggerated view from the bottom from the side of the pool, but the side that has 15 meters. So let me try this again. There we go. So the pool itself, let's say from the side view, is something like this. And I actually don't care how wide or anything that it is. If I erase this, it will delete the entire line, though. I'll try to make it seem symmetric. It really does. It's really not important. Okay, so it's 2.5 meters deep. How far does slice YK have to travel? I'm putting YK at the middle of that. What is its distance that it has to travel? Well, it goes up to here and it starts here. So that's the distance that the kth slab has to go. So, and we can see, well, basically the distance it has to travel is the length from 2.5 to y sub k. So that's pretty easy. That equals 2.5 minus y sub k. So then when I look at the work required to lift slice k is the following. I already had all this stuff at the beginning. I had 375 rho g delta y. Now I'm multiplying it by this distance of 2.5 minus y sub k, and distance is measured in meters, and we already had what we had here before. We had kilogram meters per second squared, and then I'm multiplying by another meters, so this will turn out to be kilogram meters squared per second squared. So I'll go ahead and fix that up. So this is the work done to lift slice k. So then, to lift all the slices, requires a work of, remember this thing, k equals 1 to n, and we would have all this stuff here. I'll put the delta y at the end, and you should probably put this too, since I'm talking about, well, no, delta y, I was going to put delta y sub k, but the thicknesses are assumed to be delta y for all of them, so we're fine there. So I'll have the 375 rho g, and then I'll put 2.5 minus y sub k times delta y, kilogram meters squared per seconds squared. So this will be the total work needed to lift all of those slices. Now if we want to get the exact work, I should probably put, as we always do, this is actually an approximation, usually an approximation. I will not get exactitude unless I let the thicknesses of the rectangles tend to 0. So I'll say let n go to infinity, or what is equivalent, the thicknesses of the slices go to 0. And you'll see how close it looks. Whenever we add up things whose thicknesses are going to 0, that means we're dealing with an integral. Y is the variable that we're using. Y spans from 0 to 2.5. Of course, when you go to the integral, you drop the sub k, and delta y changes to dy. Now this is an extremely simple problem in retrospect, because these are constants, rho and g are constants, so I can bring them out front. And I have the integral from 0 to 2.5, 2.5 minus y dy. And that equals 375 rho g times 2.5 y minus y squared over 2 from 0 to 2.5. The integral comes out to 3.125, so that would have been measured in meters. This stuff here was independent of the integral. I'm going to do that at the very end. This 375 rho g is the weight. This is the newt. If you want the rho g is our newtons. So we end up with 375 times rho. I already told you is 1,000 kilograms per meters cubed. Gravity we said was 9.8 meters per second squared times 3.125 meters, and what we get in the end are kilogram meters squared per second squared, or if you want, these things here can be thought of as kilogram meters per second squared times meters, and that would be the same as Newton meters. Or you could just ignore all of that and simply refer to this as joule, which the letter J is used. So you don't even need to know this stuff, to be honest, to do these problems. I'm just throwing it in there to let you know. Anyways, we multiply all this stuff out. Here's what we get for our answer. We get 11,484,375 joules. If the water in the pool of the previous example is only 2 meters deep, how much work is required to empty the pool? So here, let me go back to the integral and see how things are different this time. Here's what we have. So last time our work was 375. Now that was part of the volume. The volume of these slices did not change because the depth of the water is lower. We just have fewer slices. So that didn't change. Certainly neither of the physical constants rho or g have changed because of this. However, the y values have changed. They're only going 2 meters deep. So now the distance traveled by each of these things is not from 0 to 2.5, but from 0 to 2. Y goes, the water is where y is dealing with. Y is going from 0 to 2. However, it's still being pumped out of the pool, and the walls of the pool are 2.5 meters. So the distance these things travel is no different than before. The only thing that changed here then is this part. If it was only 1 meter deep, then you would put a 1 here. So the distance, the reason why this is the same is because the pool walls are still 2.5 meters deep. When all is said and done here, you'll end up getting 11. The reason why I'm not doing these integrals is because they're ridiculously simple. 14,700,000 joules. Now both of these first examples featured a pool where, let me back up here. Each slice was identical in nature. They had the same volume, they had the same thickness, everything was the same. What if that changes? Take a look at this. A water tank in the shape of an inverted cone is filled with water. Let me draw a picture of the thing I'm talking about here. A cone, an inverted cone, would look something like this. What we have here, let's say this is filled to the brim with water, and I know that the base radius is given by 1.5 meters, and the height of this thing is given as 6 meters. How much work is needed to pump all of the water out of the top of the tank. So how much work would I need to do? Now here's the issue at hand. We're still going to do the same thing. We're going to still slice up this cone of water, if you will. So we'll have something like this as we slice it up. But the thing is, behind there you get dashed lines like so. So I'll draw another slice up here maybe. Like that. And it has a thickness to it too, don't forget. So I'll draw. So then this be, we'll call it slice K like before. So you would start way down here at nothing. This first slice would be S1, then you got S2, S3, S4, etc. Or you could label backwards if you want. It really doesn't matter. What's going to happen then is we're going to take each of these slices and lift it up until we get to 1.5 meters. So let's take a look at a slice. I need first the volume of the slice before I can get anything else about the slice. So let's take a look at slice number K. So what we have then is, it's like this. I am going to allow, now here's an interesting thing. You may have thought about allowing your slices to be like I drew in the picture. That is, to have them conform to the shape of this. But then you'll be dealing with what they call a frustrum of a cone, which has a more complicated formula than what I'm about to do. The formula that I need is very simple, and if we slice this up in just this fashion, we get the same answer anyways. So let me try to draw it again. So like everything else, we will call the thickness of the slice delta y. Now, what is r sub k? You see, as the water gets deeper, the radius gets smaller. So how do I get r sub k? Well, the way you do it is to look at the side view. The top of the cone was at 1.5 meters. And the height, well, actually I have it backwards, don't I? I should say that the thickness of the cone was 1.5, but the height was 6. Okay, so if I took a slice of it somewhere, it's not exactly a slice, our slices are approximations. If I took this slice here, centered it at, say, y sub k, how does this radius compare with this one? So we have this 6 is the length of this triangle and 1.5 is that. Let me try to repeat what I've done here. So that's 1.5. There's 6, and then this is at y. But if I call this r sub k, and I call this y sub k, you might know from similar triangles that this width divided by that length, 1.5 divided by 6, is equal to r sub k over y sub k. Let me change this so it really looks like a y sub k. And I think I'm going to fix this picture up anyways. So when you have similar triangles, it maintains this ratio of consecutive sides. So 1.5 to 6 is the same as r sub k over y sub k. Well, 1.5 over 6 is equal to 1/4. So we can see that r sub k is actually kind of dependent on y sub k. R sub dependent, heck, it's totally dependent on y sub k. So you can see that no matter what y is, r will be 1/4 of that. So now I have what I'm looking for. What is the volume of a slice? So the volume of slice k equals, well, what is the volume of a disk? It's pi r squared times the height. Pi, and then I'll have r sub k squared, because that's the radius of that thing. And the height is delta y. Notice if r is in meters, then r squared is meters squared. Delta y is also a distance, so that comes out to be meters cubed. So it all works out perfectly fine. And then if I want the force on that disk, or that slice, remember what that's going to equal. That's going to equal the volume of that thing times rho times g, which is not that big of a deal. Let me go ahead and put those things in that I have for it. Volume times density times gravity. So I'll pull the density times gravity out as I did before. And I'll replace Vk with all of this stuff. So pi r sub k squared. I'll put the delta y at the end like I normally do. Then I'll have rho g delta y. How far does each y have to travel? Well, let's go back to my side view. And this is how high it has to go, and this is where it starts. It starts at y sub k. So then we'll take, the way I made this look is not good. Take that out. It'll be 6 minus, well, this length from the top to here is 6 minus y sub k. That's how far each of them will have to travel. So the work that I need to do to lift slice k is pi rho g. I'm pulling this stuff all out front. The r squared will stay. And then I'll have 6 minus y sub k delta y. I tried to make it a dy, but not yet, not yet. Delta y. Here also is where I'm going to replace r sub k with 1/4 y sub k. So I'll have pi rho g 1/4 y sub k squared times 6 minus y sub k delta y. This is y squared over 16, so I'll pull all that stuff out front. I'll have pi over 16 rho g y sub k squared times 6 minus y sub k delta y. And now hopefully you know the game. To find the exact work done to lift all of the water out, I'm going to integrate all these wk's. So the work will equal the integral. Well, before I put the integral, let me put my constants out front. Pi over 16 rho g. The integral, well, the water goes, since the cone is filled with water, the water goes from 0 to 6 meters. And then we'll have this stuff. Y squared times 6 minus y dy. So you can see where the yk's changed to y's, delta y changed to dy. And I won't bore you with the computations, but this turns out to be 66,150 pi joules.